Okay, in this system we've got this bar that has these two equal and opposite parallel forces applied to it. Now note that in reality this bar is not in static equilibrium. It's not a stable system. It has only a pin down here at point A, and so it would spin. So we're only looking not at equilibrium, but we're looking at a statically equivalent system in terms of the applied forces only. In other words, we're building up our skill set to getting to some more complete problems. Right, so we have a force couple system, and we want to replace it with an equivalent system, equivalent couple that is applied at B. Right, so let me lay out what we're trying to do. And here's our pin down at A, and here's the point B. And what we're being asked to do is replace this couple that comes from the two equal opposite forces. That's why they call it a force dash couple. Some people just call it a force couple without the dash. And replace it with an equivalent couple. Now this force couple from the 40 newtons wants to spin things in a clockwise fashion. So we would end up with that right there, that moment. Okay, so now note here, we can do this in a couple of different ways. We could just sum the moments of these two forces about point B, do it that way, and well, you know, that's not such a bad way to go, I guess, because look, one of the 40 Newton forces does go through that point. So when we do that, we don't really have to deal with that one. We can come along here and note, now we have a right triangle, but we have to find that distance. B to C is 270 millimeters. We need to find this angle here. Well, the total angle is 55, and the force is down at 20, so that angle is going to be 35 degrees. So since the hypotenuse is 270 millimeters, then all we have to do to find D is then say, hey, D equals 270 millimeters divided by, no, it's not either divided by, it's multiplied by sine, boy, I'm getting this all messed up. We're opposite of the angle, so sine of 35. 200, the long one, we're going to come up with a short one. 270 times 35 degrees sine equals 154.865. That's plenty there, millimeters. Right, so now we can go find M, which is just going to be F times D, and so that will be our 40 newtons times 0.5486 meters. Notice I did an automatic conversion over. More common to have answers in Newton meters than Newton millimeters. Now we end up with 6.19 Newton meters, and of course that's in a clockwise arrangement, right? And that's the answer to the question of let's replace that with equivalent system, is that. Now that's the same moment that would happen anywhere, right? Because no matter what we do here, these perpendicular distances that, let's say we wanted to find it about point A instead of point B, note what's going to happen here. Extend the line of action of both forces. We'd want to go find that perpendicular distance. We'd have 40 times this large distance minus 40 times the smaller distance. The 40 values would be the same, and the net would be just that effect right there. We'd be right back to that one. And so this force couple creates this couple effect that is the same no matter where we want to take the moments, on or off the body. That's why even though there's all these different names, force couple, force dash couple, just couple, they all have the same overall effect, and people are probably a little sloppy in their terminology and usage because it really doesn't make that much difference. I like to say force dash couple when I have one of these, because then I'm indicating what was the cause of it, where did it come from. as opposed to that same moment being caused because I came along and I applied a torque to the system. That's how I make a small differentiation, but it's not really crucial in our field of statics study.